What happens if we start to affect with one force or more than one force on an object makes it to rotate? What is meant by pivot? What about the law of moment of force? What about its unit? What about the principle of moments? Hello guys, today I'm going to talk about the moment of force. But first, let's mention and determine the objectives of our session today related to the updated syllabus from Cambridge. First, describe the moment of force as a measure of its turning effect and give everyday examples. Define the moment of force as moment equal force times perpendicular distance from the pivot. Recall and use this equation. Apply the principle of moments to situations with one force each side of the pivot, including balancing of a beam. State that when there is no resultant force and no resultant moment, an object is in equilibrium. Apply the principle of moments to other situations, including those with more than one force each side of the pivot. Describe an experiment to demonstrate that there is no resultant moment on an object in equilibrium. Actually, let's start about the moment of force. Let me give you an example to understand the moment of force. If we have spinner, as you see in front of you, and for example, we have knot on this place, so the spinner can rotate around. If the spinner rotate around this point, it must be affected with a force applied here, so the spinner can rotate around. Actually, this rotation may be clockwise or anti-clockwise. Clockwise in the same direction of clock's hands. Anti-clockwise in opposite direction of clock's hands. So now we have force will be applied here. So the spinner will rotate around this fixed point. This is the moment of force. What about this fixed point? Actually, this fixed point we can name it as pivot or fulcrum. Pivot or fulcrum, it is the point in which the object can rotate around. In order to calculate the moment of force, we have to multiply this force times perpendicular distance from the line of action of force to the pivot, this distance, if the force acts perpendicular. And we'll talk about it if we have an angle. So one more time, to calculate the moment of force, we have to multiply the force applied times perpendicular distance from the line of action of force to the pivot, so this distance. And we have force and distance. So what will be the unit of the moment of force? Newton dot meter or Newton dot centimeter, according to the unit of the distance. Maybe meter, maybe centimeter. So now we have force and distance. So now let's talk about an example. If we have the object here, and this will be the pivot in which the object can rotate around, and we have perpendicular force. This is the force. So now we have force, and now we have distance from the line of action of force to the pivot. If the force equal 2 Newton and the distance equal, for example, 3 centimeter. So if I want to calculate the moment of force, as I said, moment of force equal force multiply perpendicular distance from line of action of force to the pivot. So it will be equal to 2 Newton times 3 centimeter equal, it will be equal 6 Newton dot centimeter. If the distance in meter, so the moment of force will be Newton dot meter according to the unit of the distance. So this is the first thing in our session today. Here we have moment of force, as I said, equal force multiplied by perpendicular distance from the line of action of force to the pivot. Okay, so we have the pivot, as I said, it's a fixed point that the object can rotate around, and this rotation may be clockwise or anti-clockwise. Okay, this is the rule for the moment of force, equal force times perpendicular distance from line of action of force to the pivot. And this will be the unit for the moment of force. What happens if we have an angle? Let's take an example for that. If we have this problem as you see in front of you, and here we have force. The force equal 3 Newton. And actually here we have this distance and this distance. Which distance I'll use to calculate the moment of force? I said perpendicular distance from line of action of force to the pivot. This is the pivot. So this is the distance I'll use it. So here we have D. I want to mention this distance. But if we have this problem and he gave me the angle which is 20 degree, this angle, and he gave me this distance which is 4 centimeter, and he asked me to calculate the moment of force. How can I calculate the moment of force? Can I say that the moment of force equal 3 times 4? No, because this distance not perpendicular distance from line of action of force to the pivot. You have to use the perpendicular distance from the line of action of force to the pivot. So we have to use this distance. So how can I get the, if you remember, you talked about the cosine, sine, and tan. And actually we can get it from where? Trigonometry. How can? Here I can say that cosine angle theta equal adjacent over hypotenuse, but sine equal opposite over hypotenuse. So we'll use the cosine will be equal to adjacent divided by hypotenuse. So D divided by 4. So this means that cosine 20 equal D divided by 4. So in order to get D, cross multiplication will be 4 times cosine 20. So this will be the distance. And we have the force equal 3 Newton. So if I want to get the moment of force, I can say that moment of force equal force which is 3 Newton times perpendicular distance which is 4 cosine 20. So use your calculator. So we have 3 times 4 times cosine 20. It will be 11.3, round up, because it will be 11.27, so it will be 11.3. So equal 11.3, and the unit will be Newton dot centimeter. Newton dot centimeter, because the distance in centimeter. Okay? Actually, we have many examples about the moments. Using the crowbar to prise open something, turning a tab on or off, also open and close the door, and scissors. So we have many examples for moment of force. What about the principle of moments? What happens if we have more than one force effect on the object? Actually, we have to use the moment of, or the principle of moments. We have to use the principle of moments. In order the object to be equilibrium, so the total clockwise moments must be equal to the total anti-clockwise moments. Total clockwise moments must be equal to the total anti-clockwise moments. So this will be the principle of moments. So the sum of the clockwise moments equal to the sum of the anti-clockwise moments. Let's take an example to understand better. Here, as you see in front of you, a parent and child are in opposite ends of a playground. Seesaw. The parent weighs 690 Newton, as you see in front of you, and the child weighs 140 Newton. The adult sits 0.3 meter from the pivot. Calculate the distance and child. or the distance the child must sit from the pivot for seesaw to be balanced. Here we have force, distance, force. So we want to get the distance between the child and pivot. As I said, if you want to answer the questions and problems of moment of force, first you have to mention the position of pivot, because the distance will be between the force and the pivot. So here, where is the pivot? This is the pivot. He gave you the pivot. So we have to use the principle of moments. Principle of moments states that total clockwise moments equal to the total anti-clockwise moments. So here we have distance, or we have this distance and this adult. As you see, its weight 690 Newton will be around the pivot. So first, if I want to mention what is the direction of this adult, its moment will be opposite direction of clock's hands. So it will be anti-clockwise. But the child will be clockwise in the same direction of clock's hands. So this means that 690 multiplied by 0.3, because the distance will be between this point and the pivot, equal 140 multiply d. This will be d between the child and the pivot. So just we can get d as a subject. So d will be equal to 690 times 0.3 over 140. Just use your calculator, use it. So now we have 690 times 0.3 divided by 140 equal 1.5. So equal 1.5. What about the units? Here we have meter, here we have Newton, so it will be distance will be in meter, because the first distance here in meter, so the second distance must be in meter. So it will be 1.5 meter. Don't write 1.5 Newton dot meter, because this is not a moment of force. He asked you to get the distance, so take care. If he asked you to get the moment of force, it will be Newton dot meter or Newton dot centimeter. If he asked you to get the force, it will be in Newton. If he asked you to get the distance like this problem, maybe meter or centimeter, according to the question. Here the distance in meter, this is the old distance, so the new distance will be the same as the first one. So it will be in meter, it will be 1.5 meter. After that, what about if we have more than one force affecting the object? Actually, as I said, you have to mention the direction of each one of them. If it in clockwise or anti-clockwise, you have to add the forces that act in clockwise with each other, and also to add the force that acts in anti-clockwise with each other. So you can use the law of principle of moments. How can? If we have this example, as you see in front of you, we have the pivot, and here we have F1, and its distance to the pivot will be D1. And here we have F2, and its distance to the pivot will be D2. And we have F3, and its distance between F3 to the pivot will be D3. First, I have to mention, what about the direction of each one of them? Is it clockwise or anti-clockwise? For example, F1 will move or rotate in this direction, so it will be anti-clockwise. But F2, clockwise. F3, anti-clockwise. So this means that I have to add F1 times D1 plus F3 times D3 equal F2 times D2. Okay? Let's take an example to understand better. Figure 12 shows 3 toy animals hanging from a rod. 1, 2, 3 animals, as you see in front of you. The rod hangs from the ceiling by a string tied to the center of the rod. The system is in equilibrium, and here we have the mass of each one of them, but he needs the mass of the elephant. Use the principle of moments to calculate the mass of the toy elephant. So actually here we have more than one mass. But take care, he didn't give me the force. I know the force F or W equal M times G, mass times gravity. So in order to get the force of each one of them, I have to multiply this mass, which is 6 grams, times the gravity. Mass times gravity. The mass times gravity. So no need to write the gravity. We can cancel the gravity for all of them. And also all of them in centimeters. So we can cancel them to convert to meter. So no need to convert between centimeter to meter. Why? Because all of the distances in centimeter. So first I have to say that. What about the principle of moments? Total clockwise moments equal to total anti-clockwise moments. So this means that here we have this, the first object or the first animal, as you see, it will be in this direction. So this will be the anti-clockwise. And this object or this animal, anti-clockwise, but the elephant clockwise. So it's too easy. So now here we can say that 6 times its distance, which is 15 centimeter, plus bracket 4.6 times 10 centimeter equal the mass of the elephant times its distance will be 17 centimeter. Just you can get him as a subject. It will be 6 times 15 plus 4.6 times 10 over 17. Use your calculator. 6 times 15 plus 4.6 times 10 divided by 17 will be equal to 8. So equal 8. What about the units? The mass in gram. So it will be in gram. So it will be 8 grams. That's it. Equilibrium defined. Actually, the term equilibrium means that the object keeps doing what it's doing without any change. The object keeps doing what it's doing without any change. This means that if the object moves with a constant speed, it will continue moving with a constant speed. If the object is stationary, so the object remains stationary. So that will be the meaning of the equilibrium. So if I want to mention if this object is in equilibrium or not, I have to mention two factors. In order the object to be in equilibrium, all the forces that affect on this object must to be equal 0. This means that the resultant force equal 0. The net force equal 0. I mean the forces affect on the object. 2. All the moment of forces that affect on the object also equal 0. So here the above conditions require two things. The forces on an object must be balanced, so there is no resultant force. As I said, the total forces affecting the object must be equal 0. And the same thing, the principal of moments. The sum of the clockwise moments on an object must be equal to the sum of the anti-clockwise moments. So here we have two conditions. If the two conditions present, so the object is in equilibrium. For example, if we have this car, as you see, this car moves with a constant speed. So we have two forces affect on this car. We have thrust force and we have air resistance or drag. These two forces equal to each other. So the car moves with a constant speed. So now the car is in equilibrium. And also here we have this seesaw. As you see, we have the clockwise moments equal to total anti-clockwise moments. So that it will be remains balanced. So this will be the balanced moments as you see in front of you. And now we want to demonstrate equilibrium. Actually, this is an experiment to demonstrate the equilibrium. As you see in front of you, we have Newton meter. And actually, we can use the Newton meter to measure the force. Here we have how many forces? We have F1, F2, F3, and F4. This is the pivot. So this will be the pivot here. So first I have to mention the direction of each force. If this force acts in clockwise or anti-clockwise. For example, here, F1, it will act in this direction, so it will be anti-clockwise. So F1, anti-clockwise. And what about F2, anti-clockwise? But F3, anti-clockwise. But F2, clockwise. F3, clockwise. So this means that the sum of the clockwise moments equal to the sum of the anti-clockwise moments. Just get the result of each one of them, the number, you will obtain this result. The sum of the clockwise moments equal to the sum of the anti-clockwise moments. Center of gravity or center of mass, the same thing. Center of mass, the same thing of center of gravity. Our objectives are: state what is meant by center of gravity, describe an experiment to determine the position of the center of gravity of an irregularly shaped plane lamina, describe qualitatively the effect of the position of the center of gravity on the stability of assembled objects. First, what is meant by center of mass? Actually, center of mass or center of gravity, it is the heaviest point of the object. Heaviest point of the object or in the object. So we can define the meaning of the center of gravity or center of mass. It is the point in which the whole weight of the object may be considered to act. It is the point in which the whole weight of the object may be considered to act. For example, human, what about the center of gravity? The heaviest point, maybe here or here or here? No, here, because this will be the heaviest point. So that will be the center of gravity or center of mass. First, we have to mention the type of object in order to get or to determine the center of gravity of this object. We have regular object and we have irregular object. If we have a regular object, so the center of gravity or center of mass will be in the middle, the point of symmetry. For example, here we have 4 regular objects, so the center of mass or center of gravity will be in the middle of each one of them. This will be the center of gravity, center of gravity, center of gravity, center of gravity. What about if we have irregular object like plane lamina, as you see, this yellow object? I want to mention the position of center of gravity or center of mass. Actually, I use the plumb line. And by the way, this will be the plumb line. Just string and small weight. String and small weight. First, I'll start to suspend this lamina at any object or at any point. And after that, I'll use this plumb line. After I leave the plumb line to settle, then I'll start to draw vertical line by using your pencil. So this will be the first thing. The second thing, I'll start to suspend the lamina at another point, like this point. And I repeat what we said. I'll use the plumb line. After allowing this plumb line to settle, I'll start to draw by using your pencil vertical line downward. The intersections between these two lines, this one, will be the center of mass or center of gravity. So now I can mention the position of the center of gravity if we have regular object or if we have irregular object by using the plumb line. Stability. If I want to mention if this object is stable or not, I have to mention the relation between center of mass and its base. What does it mean? This means that if the center of mass or center of gravity above its base, so this means that this object is stable. But if the center of mass or center of gravity not above the base of the object, so this means that this object not stable. How can? If we have this object, this cross is the center of mass and this will be the base. As you see, the center of mass above its base. So this means that this object is stable. But here, the center of mass or center of gravity, if we start to draw vertical line downward, so this line will be not above the base, out of base. So this means that this object will topple over, not stable. So take care about it. Another example here, if we have this object, this will be the center of gravity and this will be the base. The center of gravity or center of base above the base, right? Center of gravity above the base. So the object is stable. If I start with to affect with small force, the object will not topple over. But here, if we have more force will be affected, the object will be topple over. Here we have another object. We have this point, which is the center of gravity or center of mass. And here we have wide base. So this object more stable than this object. If I want to compare between which object is more stable, this is more stable. Why? Because it has wide base and low center of gravity. Wide base and low center of gravity. And this is why the racing car must be wide and its center of mass or center of gravity must lower to the ground, because to be more stable, So this is what I said. Thank you so much, guys, for attending our session, and see you next session, inshallah. Happy weekend.